In this video, I'll show you how to do the ray tracing for the three types of spherical mirrors that we talked about in class. So first, I'm going to go over this idea of a concave spherical mirror, and we're going to look at the case where the object is outside the focal point. So it's not in between the focal point and the mirror, but it's outside over here. And I'm going to go through these three rules for drawing rays that I talked about in class. So let's begin. If we've got our object there, the first ray that I want to draw is a blue ray. And this is going to be in parallel and then out through the focal point. So we imagine light being emitted by the tip of this candle, and some of the photons will travel parallel to this optical axis, and then it'll run into the mirror right there. And when it runs into the mirror, it's going to bounce off of the mirror such that it goes through the focal point. So it'll look something like that. So that's the first ray. The second ray I'll draw in green. And that is going to go into the middle where the mirror meets the optical axis and bounce out of the middle. And so that ray is going to do something like this. Go right into there. And because at that spot where the mirror meets the optical axis, locally it is approximated by just a flat mirror, the angle it comes in at has got to equal the angle it comes out at. So it's got to come out at roughly the same angle. Something like that. And these sketches are just going to be approximate. It's a good way to get a rough idea of what's happening. And now the last ray that I'll draw is point number 3 down here, through the focal point and then out parallel. So we imagine photons of light, little particles of light, coming from the tip of this candle, going right through the focal point like this. And then when it hits the mirror, because of the geometry, it's going to bounce out something like that. Again, not a perfect drawing, but you get the idea. And so what that means is this spot where they all intersect right here, that is going to correspond to the tip of the candle here where the photons are coming out of. And in truth, you only need 2 of these rays to determine where the object or the image will be, but drawing 3 of them is a good idea. So right here is where we get the tip of the flame, and so we get an image that looks something like this. So that's our candle. So this image would be a real image and it's inverted. So it's real and it's inverted. How do I know it's real? I know it's real because if I took a little card of paper here, and put it right there, I would actually get photons coming from the tip of the candle arriving at that card. So I'd see a little flickering flame on that note card if I put it there at that spot. The other thing is it's in front of the mirror. It's not behind the mirror. So this leads it to be a real image. The other thing that leads it to be a real image is that these rays are converging together and that they're straight lines. They're not dashed lines, as I'll show you in some of the other examples. Okay, so this is the concave spherical mirror. The object is outside of the focal point. Now we're going to look at a concave spherical mirror where the object is inside the focal point. And by that, what I mean is it's between the focal point there and the mirror, okay? So we're gonna draw the rays just as I've outlined here with the 3 rules, and we'll do it in the colors that I've given. So we'll do blue, in parallel, and then out through the focal point. Okay, so this ray is gonna come in parallel to the optical axis. It's gonna hit the mirror, and then it's gonna go out through the focal point, like that. So that's our first ray. The second ray we'll do in green. That's the easy one. It's just into the middle and out of the middle. So it goes right in like this, and it's going to bounce out at approximately the same angle, something like that. Okay? You might go, wow, this is crazy. These lines are never going to intersect. Well, we'll get to that in a minute. We'll show you why that happens. And now we'll do the last one. So it's going through the focal point, and then it goes out parallel. Now this cannot actually go through the focal point. So if I've got, I could go through the focal point. Let me just show you this. I could take photons from the tip of the candle and make them go through the focal point, kind of like that. I could do that, but that's not going to be helpful to me. What is going to be helpful is if I basically act as if it's coming from the focal point, okay? It's going to hit the mirror. So you can see here, hopefully this little dashed line will show you, it's as if these rays are coming from the focal point. It hits the plane of the mirror, or near where the mirror is, and then it goes out parallel to the optical axis, like this. Now, if you're an observer over on the left, which I'll represent by this little eye, with the lashes. If you're an observer, what your eye does is it's going to see all these rays, and it's going to try to basically trace them back. It'll trace this one back, something like that, behind the mirror. It'll trace this blue one back to be something like this, behind the mirror. And it'll trace this green one back to be something, roughly like this, behind the mirror. It's not a perfect drawing, but you get the idea. So somewhere in this neighborhood here, all those rays intersect. And if they intersect there, then what that means is that we're going to have an image of the candle. Oops, let me take that guy back. Let's just do this, draw it in black. We're going to have an image of a candle that looks something like this. It's going to be a little bit bigger than the candle we had before. So this is the image, and this over here is the object. Okay? So your eye is going to reconstruct where these lines were coming from. It's going to say this blue one, I trace it back to there. This green one, I trace it back to there. This red one, I trace it back to there. So the tip of the candle must be right around there. And so in this case, when the object is inside the focal point, between the focal point and the mirror for this concave spherical mirror, what you'll get is an image that's actually enlarged. So it's larger, so it's enlarged. It's also virtual, and it's upright. So these are the features of that kind of image. And let me just mention a little bit more about the idea that it's virtual, because people are puzzled about that. The rays don't actually converge. As I said, it looks like these rays converge there because they're actually behind the mirror. So here's the mirror right there. And these rays don't actually travel behind the mirror. The mirror is opaque, so there's no way that photons could actually arrive at this point behind the mirror. Your brain thinks that's what happens because the rays look like they're coming from that spot. That's the main reason why it's a virtual image. Another reason why it's a virtual image is because the solid rays on the left side of the mirror do not converge, okay? The other reason is it's on the other side of the mirror, okay? So it's on that side of the mirror, so you can't have photons there. And in the convention that I'm using here, we use dashed lines. And so if we have dashed lines, when they intersect, you're going to have a virtual image. So hopefully these are reasons why you can see, based on the things that we've talked about in class, that would be a virtual image. It's enlarged, it's virtual, and it's upright. And that's different from what we got here. When the object is outside the focal point, what we get is it's real and it's inverted. Now, it could be enlarged or it could be shrunk depending on the distance where you have the object. We'll get to that later when we talk about the equations. Now let's talk about a convex spherical mirror, okay? And so now the focal point is on the other side, like that. And so it's bulging outward, it's convex, okay? Let's go through the different rays, and we'll trace them just as we did before. So the first ray, number one, is in parallel out through the focal point. So we go in parallel to the optical axis, and when it hits the mirror, it behaves as if it's coming from this guy here. So it's going to come out like that. It's going to bounce off that way. And so it bounces off looking something like that. So that's the blue one. The next one is the green one. And that's into the middle and then out of the middle. So it goes right into the middle and it comes out at approximately the same angle, like that. Okay. And let me just make a point here. 2 rays are enough. So I could trace this one back. I could trace this back. And I could also trace this one back. Right there where they intersect, that will be the tip of the candle, okay? I'm going to draw the last one, number 3, which is in red, just to show you how it should agree, okay? And now through the focal point and then out parallel. So what this is going to do is it's going to aim as if it's going through the focal point. So let me just draw this right here. So the dashed line that I'm drawing here is it's aiming through the focal point, okay? So that's where the red one's going to go. It's going to go that way. And it can't reach the focal point, so once it hits the mirror, it has to bounce out parallel, right, like that. And if I trace it back, it goes back to that spot as well. And so what that does is that leaves us with an image that is going to be a little tiny candle right here, okay? And so this is the image. And as you can see, it's constructed basically from an observer over here. They're going to see it. They will infer that these lines are all originating at some point behind the mirror. Okay, so that means that these lines, these solid lines, are not actually converging on the left side of the mirror. They're converging on the right side of the mirror. This means the image will be virtual. And there are no photons on that side of the mirror. If I took a little index card and put it over here, I wouldn't see a flame flickering on that index card because these are just imaginary extensions of the rays. The actual photons are only being carried by these solid lines. That's where the actual photons travel. There are no actual photons back there, so that's why it's virtual. The other thing about it is it's upright. And if it's in a convex spherical mirror, it will always be the same size or smaller. It's only going to be the same size in the sort of infinite limit, but it's going to be smaller almost always. And these are like the rear view mirrors that you have on either side of your car, and it says, caution, objects may be closer than they appear. So when you look in those mirrors, it looks like the object is small, so your brain thinks it's far away, but because it's convex, it's actually probably closer than it looks. Why do they make these mirrors convex? Because they have a wider field of view. So you can basically, it's sort of a fisheye lens. You can see things more broadly, but they're smaller as a result of that. So just to summarize what we've gone over in this video is how to do the ray tracing for the 3 situations that we've covered in class with spherical mirrors. And the first one is concave spherical mirror, object outside the focal point, like that. The next one is concave, object inside the focal point. And the last case is convex spherical mirror, where the object will always be on the left. It can never be between the focal point and the mirror, because that would be on the dark side of the mirror. It can't do that. And so it's anywhere here, it's going to produce a virtual image like that. So hopefully this was helpful.